Okay, so this version of the this lecture is relevant for the master version of the lecture, for the V3M version. And today we are going to be concerned with input and output in Haskell. And that's the last part concerning the practical part of the lecture, where we are concerned with practical aspects of Haskell. And then afterwards, from Friday onwards, we will look at the theoretical background behind functional programming. So the topic today is input and output with monads. And so this is the topic of our lecture today. So what's the problem? The problem is that, well, input and output, that sounds trivial. In most languages, you have some read and some write statements to read data from the outside world or to write data to the outside world. Why is this worth a whole lecture on its own? Well, the problem is that Haskell is a purely functional language. So in a purely functional language, we have the problem that there should be no side effects. So we have no side effects. And that means if you have an expression and you want to evaluate it, then the result of the evaluation is always the same, no matter what happens in the outside world. So no matter how your memory looked like before, or no matter how files are looking like, or what is the input of the user, the result of evaluating an expression should always be the same. That's what we like about functional programming. So the result of evaluation is always the same, so it's independent of, well, the outside world, where the outside world means everything that is not in the expression that you want to evaluate. So the outside world are things like the user, the file system, the memory, and so on. All this should have no effect on the result of the evaluation. And of course, this somehow conflicts with the concept of input and output, because, I mean, typically you want to read input from a user. You want to ask the user something, and the user types on the keyboard, and, well, depending on how the user behaves, he or she can type different things. Or you might want to read from a file, and depending on the actual content of the file, well, the result may differ. It may depend on the outside world. So the problem is input and output, they are desired side effects. So how can we combine this nice view of the world, this referential transparency, as it's called? So this is called referential transparency. Transparency. How can we combine this with the fact that input and output are desired side effects? So we would also like to have input and output, but we would like to maintain referential transparency. So the question is how to combine both. And the solution is we use so-called monads, and we use a so-called input-output monad. And that's what I'm trying to introduce in this lecture. So the problem is, if you had a function which reads a character from the keyboard and then returns this value of the keyboard as its result, then this would violate referential transparency. So this is something we should keep in mind. So a function that allows input, so that reads a character from the keyboard and returns this character as its result, such a function should not be possible, because the value of this function would depend on the outside world. It would depend on what the user types, and returns this character Such a function we will not write because this would violate referential transparency. So something like this is not possible, but how can we do input and output nevertheless? Well, okay, so the solution is we use this I/O monad, and let's introduce this step by step. And what we have is there is a predefined data type in Haskell, and the first predefined data type only concerns output. We will extend this to input afterwards, but let's start with output. So there's a predefined data type with the name I/O empty tuple, so I/O and then opening and closing round parentheses. And this is a strange looking data type, but why it is called like this we will see. And the objects of this data type are actions. So they are not numbers, they are not lists, they are not functions, they are actions, output actions. So the objects of this type are actions. And if you want to evaluate an expression of this type, then this means that the action which is described by this evaluation is performed. So evaluation of an expression or of a term of type I/O empty tuple. This means that the action that is described by this term, this action is performed. So this means that the action which is described by the term is really performed. Okay, and well, you can only work with this type using some predefined operations. So there are some predefined operations of type I/O empty tuple, and you can use these predefined operations. And one of these predefined operations, well, let's look at the simplest one first. So there's, for example, a predefined function which is called putCharacter. So there's a predefined function which is called putCharacter. And the type of this function is the following. It's a function that takes a character as an input. And, well, the goal is to print this character on the screen. So putCharacter gets a character as input. And what's the result of it? Well, the result is an action. It's an output action, namely the output action to print this character on the screen. So the result is of type I/O empty tuple. And, well, this is the type of output actions. So these are actions that have nothing to do with input, but it's the type of output actions. And, well, now you can, for example, in your Haskell interpreter, you can write putCharacter, and then you write a character. And to make sure that it's a character, you have to put it into these apostrophes. So if you write this, then this means putCharacter is applied to this character, to the exclamation mark. And if you evaluate this expression, then the corresponding action is performed. And, well, the action is that the exclamation mark is printed on your screen. Well, that sounds amazing. But, well, it'll get more amazing in a minute. OK, so there are some predefined operations like putCharacter which allow you to do some output things. Now, of course, you want to create your own output actions. And how can you do this? Well, you can take these atomic output actions and put them together, glue them together. So there are some more predefined operations. For example, there's a predefined operation called then. So there's a predefined function then. And this is an infix operator which is written in this way. So it's a double greater. And this double greater has the following type. It glues two actions together. So it's more or less the performing two actions after each other. So to have some kind of sequentiality between actions. So this takes one action and another action. And it gives you back the action that does the following. It It first does action 1 and then it does action 2. So this is, well, gluing two actions after each other. First do this and then do this. So let's make an example. So let's create a new action. For example, the following action: put character A and then put character B. So what's this? This is an action. The action is composed of two atomic actions, namely this one and this one. And if you execute this in your Haskell interpreter, you can imagine what will happen. It will print A and it will print B. So you have AB. That's more amazing. So this thing is pronounced then. So you don't say greater, greater, you say then. So put A, then put character B. Okay, one more predefined function, and then we'll start writing more sophisticated algorithms. So we now know atomic output actions like put character. We know how to glue them together in a sequential way. Well, one last, at first sight, not so useful action is the empty action. This is the action that does nothing. And so there's another predefined function, and this is called return. Return empty tuple. This thing also has the type IO empty tuple. It's also an output action. It's the output action that does nothing. So this prints nothing on the screen. So this has type IO empty tuple, and this is in some sense the empty action. So this is the action that does nothing. So in other words, if you say put character, let's again write the exclamation mark on the screen, and then return empty tuple. Well, this is a new action which consists of gluing together this action and this action. And since this is the empty action, it does nothing. So if you execute this, if you evaluate this, then these actions are actually performed. And so the exclamation mark will be printed on the screen, and that's it. OK, so now let's write a more sophisticated output algorithm, put string. So the idea is not put character, where you put a single character on the screen, but put string should print a whole string on the screen. This is predefined in Haskell, but if it weren't predefined, we could define it ourselves. So the goal is now, let's write a function putString. And the goal is that putString should take a string as input and print it on the screen. How would you do it? So what's the type of putString? Well, it's a function, and it takes a string as input, right? So it takes a string as input. And what's the result? What's the result type? IO empty tuple, because IO empty tuple is the type of output actions. So it should map a string like hello to the output action which prints the string hello on the screen. OK, so now let's define it. This is the type declaration. Now we have the function declaration. And the nice thing about strings in Haskell is they are just lists of characters. So we can do ordinary pattern matching on characters. On lists of characters. So there are two cases. Either the list is empty or the list is non-empty. If the list is empty, what should happen? Return. Return empty tuple. So this empty action is useful because as soon as we have recursive definitions, it's really nice to have something for the empty action. So if we have to print the empty string, well, then there's nothing to do. So then we use this empty action. And if the string is non-empty, put string x:axis. So x is the first character, and this is the list of the remaining characters. Then what will we do? Put character, right? So put character. So the first character that we want to print is x. And now, then, right, put string axis. So this does the right thing. So you can write algorithms on this with these actions. So as you can see, this is the data type like any other data type. So you can write functions that operate on lists and give you backsection action. You can treat these actions like anything else. You can also have lists of actions, functions on actions. Everything is possible. And so this gives you an idea how to create output actions. But of course, input is even more interesting. But typically, you want to read something, do something with it, and print it out again. Yes?
In your examples, which are exclamation mark and return, if you turn these two actions around, if you dot it to return and then sharp,
same thing happens.
Get the same thing.
You get the same thing.
Okay.
So read.
Because from C and Java, you can expect that don't have all actions that come after.
No, that's not the case here. So return does, okay, so the return in Java or C stops the execution of the actual method and returns to some program that called this method. This is not the case here. So this return means, well, return nothing, but it does not stop the evaluation. So indeed, if you turn this around and you first say return empty tuple and then put character exclamation mark, then it will print the exclamation mark. So return does not end the evaluation of the program. Okay, now let's move on to input. So now we want to read something from the keyboard. We know how to print something to the screen. Now we want to read something. And, well, similar to the function put character, there's also a function get character. And the idea is that, well, this IO empty tuple, this is the type of output actions. But if we want input actions, they also need to have some type. And so in general, after this IO is a type constructor, so like a list or things like that. It takes a type as an argument and creates a new type. And the argument type doesn't have to be empty tuple, but it can also be another type. So in general, we may have types IOA, where A is an arbitrary type. And this means this is the type of input-output actions which, during the action, compute a value of type A. So this is the type of in or output actions which determines a value of type A. Of type A. And if you have a pure output action, well, then this does not really determine any value. And as you might remember, this is the type of, this empty tuple type is also a legal type, and it has just a single element, namely the empty tuple. So this makes clear that the value that is determined here is, there is no real value determined here, because the only value of this type is empty tuple. So this means nothing is really determined here. This is a pure output action where no input takes place. But if you want to have something like get character, which reads a character from the keyboard, then indeed a value is determined, namely the character that the user typed in. So get character is also an action, but it has the type IO character. So, so there's a predefined function called getCharacter. GetCharacter, or it's a predefined, well, it's not a predefined function, it's predefined. And the type of this thing is IO character. So in other words, this is also an action, but this time it's not of type IO empty tuple, so it's not a pure output action. It is more an input action, because here, if you evaluate this, the action is performed, and it's the action read a character from the keyboard. So this waits for the user to type something, and if you type something, then this character is determined. So this is the action that reads a character from the keyboard. From the keyboard. And you can also depict this graphically. So the value of get character is an IO action. And in this IO action, a value of type A, or in this case, a value of type character is determined. So this depicts an IO action where a value of type A is determined. Or sometimes one also says it's encapsulated in this action. So it's determined or encapsulated. So what is very, very important is that the value of get character is not the character that the user has typed. The value of get character is the action to read the character. So the value of getChar is not the character which was typed in by the user, but the action to read a character from the keyboard. From the keyboard. And this is very important because, well, referential transparency means that if you have the same expression twice, well, then the value of the expression is always the same. So the value of get character is always the same. The value is the action to read a character from the keyboard. But of course, one time the user can type the character A, and one time he or she can type the character B. But still, the value of get character is not A and it's not B. It's the action to read a character. And this action is always the same. So, well, we will make this clearer with some examples in a while. So to make clear, to use this get character in some in some program, let's also extend the function return. So up to now, I said that return empty tuple is the empty output action. Well, in reality, return is a bit more flexible. So this predefined function return in reality has the following type. It's a function that takes a value of type A and gives you back an IO action where this A is encapsulated. So in other words, this return takes some value and gives you back an empty action which does nothing, but where this value that you gave as an argument to return, where this value is encapsulated in. So this is the empty action which determines or encapsulates the value given as argument to return. So this is the real type of return. And also this function then, which we can use to glue actions together, in reality has a bit more flexible type. So this predefined function then, in reality has the following type. So it can start with an IO action that determines a value of type A. The second argument is an IO action that determines a value of type B. And the result is an IO action which also determines a value of type B. And to depict what happens here, we can look at the graphics. So the first IO action determines a value of type A. So it looks like this. You can think of this as, for example, taking get character, and get character determines a value of type char, so a value of type character. And so this is the first IO action. The second IO action determines a value of type B, and then means that you create a new action which first does this, then it throws the value that was determined here away. It simply ignores it. Then it performs the second action, and the value that was determined in the second action, this is the value that is determined in the composed action. So this, if you compose them, it does this. It first does the first I/O action, ignores the value that was determined here. Then it does the second I/O action, and the value that is determined in this composed I/O action is the one that was determined here. So in other words, if you have one action P and you have another action Q, then the result is the action that first performs P, ignores the value determined by P, determined by P, and then performs Q. So to give an example, I have to wipe the board. Okay, so let's look at an example. Let's take get character, then return empty tuple. Is this okay? Well, this thing is of type I/O character. This thing is of the type I/O empty tuple. And so the whole thing is of the type, well, it's the type that is taken by the second action. So the type is I/O empty tuple. So what does this do? Well, it performs these actions sequentially. So it starts doing this action. So it reads a character from the keyboard, then it ignores this character and does the empty action, so it does nothing. So this reads a character from the keyboard and then throws it away. Now that's not a very useful action, but this is what it does. So reads a character from the keyboard and ignores it. And ignores it, because the problem is with then that the value that is determined, that is encapsulated in the first action, is discarded. It's simply ignored, and one only regards the character that is determined in the second action. So that's not so useful in this case. It would be nice to do something with this character that was typed in by the user. So for example, you might want to have something that reads a character from the keyboard and then prints it on the screen. That would make sense. And to do this, there's another way to glue actions together beside this, this operation then that we've seen before. And this other operation is called bind. So there's another predefined function which is called bind, and this is written like this, so greater, greater, equal. And what's the type of this? So the first argument is also an action where we determine a value of type A. But the second argument does not ignore this value, but the second action depends on the value that we have determined in the first action. So the second is a function. Depending on the value that we have determined here, it performs a certain action. So the second thing is a function which goes from A to IOB. So it's a function that maps, depending on the value that was read in the first action, we perform a second action. And then the result of the whole thing is an action of type IOB. So if you want to depict this graphically, it looks like this. So the first action is something like this. It's the first action, and here you determine some value of type A. And then we bind this together with a function. So it's a function. Let me depict it like this. It's a function that waits for a value of type A. Depending on this value, it does another action, IO2, which determines a value of type B. And binding means I glue them together. So binding them together means I do the action 1, I determine a value of type A, and depending on this value, I do another action, and in this second action, I determine a value of type B. Okay, let's do an example. Let's define a function echo, which reads a character from the keyboard and then prints it on the screen. So in the end, well, echo reads a character from the keyboard and prints it on the screen. So in the end, this is a function. This is an action where nothing is encapsulated anymore. So it looks like a output operation. And how is this defined? Well, first we do get character. And get character is of type IO character. So this is an action which reads a character from the keyboard and, well, it determines this character. And now, afterwards, we bind this to a function which takes out the character from this action. So it takes the character that was determined here and does something with it. Namely, it prints it on the screen. So we do put character afterwards. And put character is a function that takes a character and produces an output action, namely the output action that prints this character on the screen. So if I bind them together, then indeed I have an action which first does this, so it reads the character from the keyboard, then it takes this character and prints it on the screen. So this is the action which reads a character from the keyboard and prints it on the screen. So you can see that this bind operation is really useful. Now, suppose that I want to read two characters from the keyboard and print them on the screen. So I want to do echo twice. How can I do that? So, yes? Echo, then echo, right. So if I say echo, then indeed this reads, so this lets the user type one character and prints it on the screen and another character and prints it on the screen. So this reads two characters and prints them on screen. Now what about this? That depends, in fact, on your Haskell implementation. So I tried this out with GHCI on Linux and Windows, and they behave differently. So one version did one of these things, and the others did the other. If you compile this, then hopefully it has the same operational behavior. What about this? How many characters will this read? One or two?
One.
Who thinks one? Who thinks two? Who thinks one? Who thinks this will read two characters? Democracy wins. So the majority was right, so this reads two characters. Because x has the same value all over here. And the value of x is not the character that is read. The value of x is the action to read a character and print it on the screen. So everywhere where x occurs, this is the action read a character and print it. So here, read a character and print it, and here, read a character and print it. But so it reads two characters. It does it here, and it does it there. So the value of x is read character and print it, and it's not the value of the character. So this really reads two characters and prints them both. Reads character and print it. So it doesn't matter whether I write this or whether I write this. This does the same thing. That's what you would expect. I mean, X now is a local declaration. Everywhere where X occurs, it should stand for echo. So if you write this or if you write this, it should do the same thing, and it does the same thing. So this is really, these two things are equivalent. So indeed. So this is what I mean by referential transparency. Every time echo occurs, it has the same value. It's always read a character and print it. But the value of echo is the action to do this. It's not the character that the user has typed in. Yeah?
How would you write a function that reads two characters and then just returns them? So you read a sequence of characters without outputting them. So echo reads one character and outputs it, but what if you want a sequence of them?
Okay. Give me 5 more minutes and then I'll do it, okay? Okay, so the question was, how can I read not just one character and then print it, but I read 2 characters? In fact, I'll give you a function that reads n characters. You give me the n, the function reads as many characters as you like. Yeah, I will show you.
How can you create a function that reads one character and prints it twice?
How can I write a function that reads one character and prints it twice? Okay, also good question. So keep your questions in mind, wait 5 more minutes, and then we will do it. Because before I want to, I will write some algorithms with these bind operations, and then we can write all of these things. But before I do this, let me highlight the connection between then and bind. And bind is much more general. So if I have bind, then I can program then myself. So then can be expressed with bind. Why? Well, if I want to have P, then Q, this just means ignore the value that you computed during this action and perform this action afterwards. And I claim that I can also do this with bind. Now, after bind, I now need a function. This has type IOA. This has type IOB. So here I need a function that takes a value of type A and then performs Q. So I can simply take the function that takes the value of type A. I can call it X, but since I don't need this value, I call it underscore. So it takes this value but ignores it and then does Q. So this is a function, in this case, of type A to IOB. And so this thing and this thing do the same. So then just means ignore the value that was determined here and do this other action. Okay, before we do all these algorithms that do the things that you just proposed, let me give 2 more predefined functions because otherwise I will forget it. You've seen that you can interact with the keyboard and the screen. And in the same way, you can now also interact with files. So there are some more predefined functions. And I will just mention 2 more of them. There's a function read file and a function write file. And they allow you to do input and output with files just as you do it with the keyboard and the screen. So read file is a function of type string to IO string. And the idea is that the argument that you give here is the name of a file. And then read file reads this file. Well, the read file, OK. So if I say read file of some file name, this is the action which reads the file called my file. And the value that is determined in this IO action is the content of this file. So in this file, there is some long string, and this string is encapsulated in this IO action. And the determined or the encapsulated value is the content of this file. And similarly, there's also a function writeFile. And writeFile takes as first argument the name of the file. The second argument is the desired content of this. So you want to overwrite the previous content of this file by some new content. So the second argument is the new content of this file, and the whole thing is an output action. So the value of this is, so writeFile with the arguments, here you have a file name, and here you have some new content, for example, the string hello, and the value of this is the action which overwrites the previous content of this file with the word hello. So then afterwards in your my file you have the word hello. So it's the action that writes hello to my file. So the same concept as for input and output with the screen and the keyboard. Okay, now back to your questions. How can I write interesting programs? So the first question was what happens if I don't want to read just one character, but I want to read two characters without printing them out in between? So let's do this. And let's do not only reading two characters, but let's read n characters. So let's write a function gets. And gets doesn't only get one character, but it may get 2 or 3 or 4 characters. So it's a function that takes an integer, and this integer determines how many characters you want to read. So gets 2 would read 2 characters. So what should be the result type? Well, it should be an action, so IO. And what will be the type that I want to encapsulate here? A string, right. I want to encapsulate not just a character, but I want to encapsulate a whole list of characters. So, okay, so gets n. If I call gets with some number n, well, let's first check whether n is greater than 0 or not. So if n is 0 or negative, if n is smaller or equal than 0, then what do I want? Then I want to do nothing, right? I mean, no real action should take place because I don't want to read anything. So I want the empty action. The empty action I can produce with return. And what do I want to encapsulate in this empty action? So what is the string that I have read now? The empty string. So I take return and I encapsulate the empty string. And this indeed has the type IO string. It's the empty action where this value has been determined. Okay, so this is what's happening if n is negative. Now, if n is positive, then I really want to read. And now how do I do this? Well, I have to read one character after another. And the only atomic function that we know for reading characters is getCharacter. So let's start with getCharacter. And now, by doing this, I will read one single character. Now, I should not forget this character because this will be the first character of the string that I want to encapsulate in the end. But I have to read more. So I will need recursion. I mean, I will have to call gets with n-1 because now I have read one character. So there are n-1 characters that I still have to read. So let's keep this character that I read here in mind. And, well, we have to use bind to not to forget it. And to keep it in mind, now we need a function. I mean, if you look at the type of bind, here we have encapsulated something of type character. So this has the type IO character. So here we need a function that maps a character, namely this character that we just had, to some action. And this action that we need is we have to read n-1 additional characters, and then we have to glue this character that we read at first in front of this list, and then we have to return the whole thing. Yeah, you have an idea?
Gets
Semicolon, semicolon sounds too imperative. Well, so I will first write it down in the proper way, and then I will show you how to write it down in a nice way. So let's first do it the hard way. So we have to keep this character in mind, and we need a function that maps this character to the remaining action. So if we need functions, we can do this by lambda. So we map this. This is a function x, and this x will then be the character that we have just read here. So x will be, so this will have the type character. This will be the character that I have just read. And now I have to map this to the remaining action. And the remaining action is read the rest. Read the remaining n-1 characters. Okay, so read the rest is, I call gets recursively with n-1. Now this gets n-1. What is the type of this? Well, gets, if I call this with an integer, it gives me an IO action where a string is encapsulated. So this thing has the type IO string. So what should happen then? So now I read this character first. I keep this character in mind. I read the remaining n-1 characters, and I should keep them in mind as well. So during this, I determine a string. So let's do bind again. And now I should keep this string in mind as well. So I need a function that takes this string that I determined here and then does something with it. So let's again have a function, lambda xs. And now this xs has the type string. So this is the character that I read in the first step. This is the string that I read in the remaining n-1 steps. And now what should be the action that I do in the end? I should return this whole thing. So in the end, I should return. And what should I return? Well, not the empty list this time. Sorry? Empty character. That would be disappointing, because then I read these n characters and then I do nothing and they are lost. That would be bad. Yes. Yes. So I should return this. This should be the empty action, but I encapsulate the string that I have read here. So I encapsulate the string that starts with this first character, and then we have the remaining characters here. So this indeed does the right thing. So this will first do this. So this whole thing is a large action which is composed of three things. The first action reads the first character, and we keep it in mind. The second action reads the remaining string, and keeps it in mind. And the last action does nothing but encapsulates the string which starts with the first character, and then we have the remaining ones. So this is possible, but everyone agrees that this looks horrible, right? Wow, okay, you can understand it, but it looks a bit, well, you have to get used to it. It would be nicer if you could write this like in imperative programming. And, well, you can write this as an imperative programming, because in Haskell, there's syntactic sugar for this. So if you don't like this notation, there's a notation which looks like an imperative program, but it's just a shorthand for this. And this notation for the imperative program, I want to show this to you next. So if you look at this program, this gets, yes? How can we append a certain string to a file? Okay, maybe there are more elegant versions, but one version is you read the content of the file, you append your new string to this thing, and then you write it again. So,
but if the file is large, then
it takes long. Yes. Okay, maybe there's also a predefined function which doesn't override but appends it in the end or in the beginning. I don't know. So, I mean, there are many predefined functions, and I don't know them by heart. So it could well be that there is a function like this. Right. Okay, let's go back to gets. So this is a very general pattern that you see here. We do something, we determine a value, and we want to keep this value in mind. We want to we give this value a name, we call it x, and later on we want to use it because it will be needed for our overall result. Similarly here, we compute a value, and in some sense we store it in this variable x's, and we need it afterwards because we want to return it in the end. And so to have a nice formulation for this pattern, there's a special notation in Haskell, namely the so-called do notation. And the do notation is the following. So instead of this pattern where we have an action, and well, this action has the type IOA, so we determine a value of type A here, and then afterwards we have a function here which takes this value of type A and afterwards performs another action of type IOB. So instead of this, one can write the following. And now this looks a bit like imperative programming. There's the keyword do, and then we say, well, do this action and save the value that is determined here in the variable x. So in other words, x becomes the value that is determined in action P, and afterwards do action Q. So you can write this in Haskell, and this is translated into that. And of course, Haskell programmers dislike these curly brackets, and they dislike these semicolons, and you know that if you do the layout properly, you can omit this. So if you do the layout properly, you can also omit these brackets, and you can just write do x gets the value of P, and then we do Q. Now, in the example up there, we did this twice. So we had 2 occurrences of bind. And of course, do works also with several occurrences of bind. So instead of first do P and bind the value that you determined here to a variable x, and then do Q and bind the value that you determined here to a variable y, and then finally do R. So instead of this, one can write do, and now x becomes the value determined by P, y becomes the value determined by Q, and then we do R. And this looks already a bit imperative. So let's do it in our example before I write down the general rules for this do notation. So you see the definition of gets up there. I will now write it again, but now I use this nice looking do notation. So how would it look like then? So gets would still be a function from int to IO string. And well, if I call gets with some number n, the beginning is the same. So if n is negative or 0, if n is less or equal to 0, then I create the empty action where I encapsulate the empty string. And otherwise, I say do. And now I use this nice notation. So what happens in the first action? I do get character, and I save the value in some variable x if you want. So let x be the character that I read by get character. Then what do I do next? I call this action gets n minus 1. This determines a string of length n minus 1. And I save this string in the variable x's. So let x's be gets n minus 1. And then what do I do in the end? I return x, well, this string, x colon x's. So return x colon x's. And now if you look at this program, this looks pretty readable. I mean, this looks like you would do it in imperative programming, right? You want to read a string of length n from the keyboard. If n is negative, then return the empty string. And otherwise, read one character. So x becomes the first character. X's becomes the remaining n minus 1 characters. This is a recursive call. And then you return the string, which starts with x and then comes x's. Now, if you would write this in your favorite imperative programming language and you are forced to do it in a recursive way, this would be more or less your program. So this looks imperative, but it is not imperative. This is syntactic sugar, and Haskell translates this to this. So in reality, Haskell executes this, but of course this is much nicer to read and to write. And so if you want to program with the input-output monad or with other monads, then this do notation is pretty handy because, well, it's easy to read and easy to write. So what are the rules for this do notation? So what are the rules for this do notation? As I said, it's just syntactic sugar, and Haskell translates the do notation away. So I will write it not with this offside rule, but I'll write it with brackets because I don't have enough space to make so many line breaks here. So if the argument of do starts with something like this, and then and S is the sequence of the remaining commands in this do statement, then what does this mean? This means this is the action where you first perform P, you bind the resulting value to X, and then you do the rest. So this means if the first statement in this do looks like this X left arrow P, then this means P bind lambda X, and then continue. And if the first action does not look like this, but it's just an action without a variable in the left arrow, so it just looks like this, then this means do P first, ignore its encapsulated value, and then do the rest. Well, and if you have just a single action do P, then this means P. So if you apply these rules recursively, you can translate your do notation back into something with bind, and this is what Haskell actually does. Yes?
Means you can override variables. So if you have x, then write e, and you can later have x arrow q and override it as x.
Well, it's like with lambda expressions. I mean, this do adds nothing new. So you can have lambda x goes to something. And, well, function arrow associates to the right. So this means this. So that means all occurrences in here, all occurrences of x in here are bound by this x and not by this x. So this you could do already before. So the do notation is nothing new. It's just syntactic sugar because, well, writing expressions with bind and lambda looks ugly, whereas this looks pretty readable, I think. And, well, so you can use it, and I would use it if I have to write input-output functions, because this really looks like imperative programming, although it is functional programming. And, well, to stress this, let's again look at some examples. Okay, but I have to wipe the board once more. So what's the nice thing about this I/O monad? So the nice thing is that referential transparency is maintained. So in other words, everything that might depend on the outside world, so everything that might depend on input and output, is always encapsulated inside these I/O actions. So values depending on the outside world, like the keyboard or files or so, on the outside world are always encapsulated in I/O actions, and there is no way to get them out of it. In I/O actions. So that means if you say get character, well, then I have an I/O action which encapsulates a character, and there is no way to get this character outside the I/O action. You can do something with the character, but then you have a new I/O action as a result. But there is no function result which takes such an I/O action and gives you back the encapsulated value. So you cannot get it out. Which can give the encapsulated value as result. And this is really important because otherwise we would have this problem of referential transparency violated. I mean, if you think of it, if I do this, let x be get character in, and then you have an expression where x occurs twice. Then what will happen? How many characters will I read? Will I read 1 or will I read 2? I will read 2. The value of x is the action to read a character. So if this occurs several times, well, it's the same action, so this will read 2 characters. We'll read 2 probably different characters. So this is really equivalent to writing get character, get character. So this is equivalent to this. But if I had a function result, which does not exist in Haskell, but if this function existed, and if I would write let x be the result of get character in x, well, then I would have the problem that, well, this thing would be evaluated only once. So then I would really just read the character probably once, get a result, and this character should somehow always be the same. I mean, this x is a character, so if it occurs several times, it should be the same character. Whereas if I write result get character twice, it might be something different, because every time that I evaluate result get character, it would give me a different character. So they would probably not be equivalent. So they are probably not equivalent. So this should not happen. If an expression occurs several times, then its value should always be the same. It cannot happen that the value here is the character A and the value here is the character B. Something like this should not be possible, and therefore a function like result is not possible. So this result function is not possible in Haskell. So you really have a strict separation. Those things that have to do with side effects, they are always encapsulated in these I/O actions. And the things outside these I/O actions, they are side effect free. So all side effects are clearly separated from the non-side effect free part and I/O actions, and they are clearly separated from all other values. So this is, and well, this I/O data type is predefined. So you have no way of programming such a result function yourself. You can only, there are certain predefined operations that operate on this I/O data types, like put character, get character, bind, then return, and so on. And you can use them and you can write new functions with them, but accessing the value inside such an I/O action, that's not possible for good reasons. And well, now you might ask, what does this word monad mean? So that's something I didn't really tell you yet. So a monad is a data structure with certain properties, and the I/O monad is one example of such a data structure. So a monad is a data structure with certain properties, and I/O is one example of a monad because it has these properties, but there are other predefined monads in Haskell, and you can also define, well, you can find data structures yourself, and maybe your data structure is also a monad if it satisfies these properties. There are others, both predefined and user-defined. And user-defined. And what are the properties that turn a data structure into a monad? Well, that's what I want to show you in the end. So in Haskell, there's, I mean, you remember type classes. So if you have several somehow similar types, you can group them together in a class. And well, the same is true with monads. So there's a predefined type class called monad, and I/O is an instance of this type class monad, and there are some other instances. And you can also define your own instances of the class monad. So in Haskell, the following class is predefined. Monad. So M is a monad, and there are certain operations predefined on monads. And well, up to now, we only had type classes. So here we had a type, and then we said, okay, this type can be a member of this type class, and then there are certain functions for these types. Now, in addition to these type classes, you can also say that a type constructor belongs to a certain class. So M is not a type, but M is a type constructor. So this is not a type class, but it's a constructor class. So M does not stand for a type, but for a type constructor. So a type constructor, for example, like I/O. And so M is not a type, but if we apply M to some type, then we have a type. So MA is a type. It's a type if A is a type. So, for example, if we apply I/O to a type, then we have IOA. That's a type, or IO empty tuple, or IO character. These are types. So some type constructors are monads. Not some types are monads, but some type constructors are monads. And there are certain functions that have to exist for every monad, namely return, bind, and then. So there always has to be a function return, and there always has to be a function bind, and there also has to be a function then. And what are the types? What's the type of return? Well, the type of return, the idea is you can apply it to an arbitrary value, and it gives you back something of type, well, monad applied to A. So something of the type MA. So up to now, we had regarded only the monad IO, and then return was a function from A to IOA. If you have a different monad, return exists as well, and it simply encapsulates your value. And bind Well, up to now, we said this is used to compose two I/O actions after each other. In general, it is meant to compose one value encapsulated in the monad with another value encapsulated in the monad. So if you replace I/O by M, then you have the type. So we have one value of type A encapsulated in the monad. We have a function that takes this value A and encapsulates an object of type B in a monad, and the resulting thing has type MB, so something of type B encapsulated in the monad, and so on. And so whenever you want to declare that your type constructor is also a monad, then you have to make sure that these functions exist, and you have to implement these functions. And of course, you can implement them in any way you like. And so your function return and your function bind can do strange things. Of course, that's not what they should do. I mean, it's the same with equals. If you say my new type is a member of the type class EQ, you can implement the function equals in a strange way. But you shouldn't do it. You should implement equals such that it computes equality. And also here you should implement return and bind in the right way, namely in the way that they behave like they should behave for monads. And well, for monads, three properties should be satisfied. That's what I wrote up there. It's a data structure with certain properties. For a real monad, return and bind should be implemented in the right way. So they should satisfy certain properties, namely the three monad laws. And you can, it's not so difficult to see that for I/O, these are satisfied. And if you do it yourself, they should also be satisfied. So the first monad law says that return should be the right neutral element to bind. So in other words, if you, let's think of I/O. So if you have an action P and you bind it to return, then this should be the neutral element. So if you first do this action, then you take the element that was determined here, and then you do return, then it should be the same as P. So in other words, return should be the right neutral element for bind. And the second monad law is return should also be the left neutral element to bind. So if you first do return, so you return some x, this is of the type, a value of type A is encapsulated in this monad, and then afterwards you do some function f, where f takes this value out and then gives you back something of type B encapsulated in the monad. Then what should that be? So if you think of I/O again, then this is the empty action which determines this value x, and f should take this value and do something with it. So this should be the same as f applied to x. So this says that, well, you should really take out the element that was determined here and do something with it. So this says that return should be left neutral for bind. And the last statement says that bind should be associative. Let me probably write this down in the do notation, because this do notation is available for every monad. So not just for I/O, but for every monad. So if you define your own monad and you say my new type constructor is an instance of class monad, then you can also use the do notation. That can be convenient. So the last statement says the following. if you do the following, you say, well, I determine a y by doing the following. I first do my action P, which determines an x, and then I do Q, and then afterwards I do R. So this means I grouped P and Q together, so I first compose the actions P and Q, and then I do R. And associativity means that I could also do it the other way around. I group Q and R together, and I first do P, and then I do the composed thing of Q and R. So this should be the same as doing first P, and then I group Q and R together. So this means that bind is associative, provided that X does not occur free in this R. So if X does not occur in R. And so indeed this do notation is available for every instance of class monad. So this is the concept of monads, and well, if you want to do advanced programming and advanced functional programming, then it can be a good style to use monads for all kinds of things, not just for input and output, but also for other things. So maybe on one of the exercise sheets you had this data type maybe, and this data type maybe in fact is also a monad, so you can also use do notation for it. But that leads a bit far. Well, I wanted to show you this principal idea, and in particular you need this whenever you want to do input and output in Haskell. And as long as you use the do notation, you can do this in a rather readable way. OK, so this is the end of the lecture about monads. On Wednesday, there's exercise course, and on Friday, there's lecture for everybody again, and then we'll look at the theoretical concepts behind functional programming. So see you then.